Um, Hello to this penultimate lecture of this course. Today we want to discuss the question whether or not gravity needs to be quantized. So with this, if you remember last week, we discussed the Schrödinger-Newton equation as a non-relativistic limit of a Klein-Gordon field coupled to gravity through Einstein's equations. So a situation where we have a classical space-time with a classical Klein-Gordon field, and we take the limit, the limit where the speed of light goes to infinity, and we find that in this case we get a Schrödinger equation that also contains nonlinear self-gravitational terms. And we ask to what extent do we want to take this as a serious model, not just for a classical field on a classical spacetime, but also for quantum matter that is subject to gravity. And it comes down to the question whether or not we believe that when we quantize the field, we also need to quantize the gravitational degrees of freedom, or whether we have a fundamental description in which our quantum fields live on a classical spacetime. So this picture is called semi-classical gravity, and if you want to argue from a philosophical and or theoretical point of view, so the first thing you could ask is, well, what of our intuition about physics speaks for or against such an approach? What do we actually know about the way gravity works in theory, the way quantum mechanics works, that suggests that we should also somehow quantize gravity or not? And one way to see it is there are two different points of view from which you can look at general relativity. The one is you can take Einstein's equations and say Einstein's equations. So remember, you have on the left hand side you have the Einstein tensor, which is a function of the Ricci tensor and Ricci curvature, which again are functions of the metric. So basically this is just an expression in terms of the metric. So I maybe write it like this to make this explicit. And on the right hand side we have matter in the form of the stress energy tensor. So we can ask, like, what's the philosophical idea behind this equation, or what are we thinking about? And one way to see it is the perspective of field theory, where we say, well, this is a field equation. This is a field equation for a field h mu nu. We can also treat the curvature as a field if you want, but for the simple case, let's say that this is an h mu nu. So h mu nu is I mean the full metric. So let's call it g mu nu to be consistent with the rest of the lecture. So g mu nu is we know is a function that depends on space-time coordinates. So it's a g mu nu of x. So basically what I can say is this g mu nu is just a field that lives on space-time. So curvature, the metric, the curvature is a field on space-time. And from this perspective, I would say, well, we know what we do with the other fields. We know we have the electrodynamic field. We know we have the weak and strong interactions. We know whenever we have a field, we can use the formalism of quantum field theory, quantize this field, and work with this quantum version. And from this perspective, I would also want to say, well, gravity is somehow just another field, so let's take this field, let's quantize it somehow. This goes wrong, of course, as you might know. It goes wrong because the field theory that you get turns out to be non-renormalizable compared to, in contrast to the other ones. I will very briefly mention this later on. But it's just one point of view from which you can look at this. Another point of view would be to take the geometric aspect of gravity very seriously. So the other thing that this equation tells us, or that general relativity tells us, is that there are two things. There is space-time. Space-time is a four-dimensional manifold in general relativity, and it is basically it provides kind of the substance on which we have our other fields. So we have matter fields that live on space-time. We can only define our matter fields if we can talk about the value of a field at a certain space-time position. So we have fields on space-time, and we have this space-time itself. But now you can take general relativity, and you can take as the lesson from Einstein also to say, well, there is no such thing as gravity, in the sense as there is no field that is gravity, or there is no force, gravity. What we experience as gravity is just the curvature of this space-time. So the space-time is not flat, it's not Minkowski. The space-time has a curvature, and this curvature is it's actually more than that. It's not just curved. This curvature also dynamically interacts with the fields itself. The curvature is generated through the value of the fields. But still you have this hierarchy. You have the space-time and you have the fields on top of the space-time. And if you look at it from this more geometric perspective, then from a philosophical point of view, there is no reason a priori why we should also quantize space-time. What does it even mean to quantize space-time? This could be something completely different than what we do to matter field. So I want to make sure you are aware of this distinction. Both perspectives are perfectly valid. They are both perfectly consistent with any predictions that the theory makes. But you have different philosophical points of views here, right? You can either say, well, the metric is a field on space-time, curvature of space-time is a field that's living on space-time, and as such I quantize it. Or you can say, well, space-time is something that is completely different from matter fields, so I don't have a reason philosophically to quantize it. And now you can also look at theoretical arguments. You can say, well, what happens if I do something else? And then the first question is, what could I actually do other than taking this as a field and quantize it? I mean, this is of course what we know. Quantum field theory is a well-established field of physics, so we have a good understanding of what we're doing there. So I can take this G mu and quantize it. What if I don't quantize it? Well, I can of course work with classical general relativity. That is also very well understood. But I know that my fields are actually quantum fields. So if I want, whatever is here in quantum physics is actually an operator. And this equation doesn't make sense anymore. So we have on the right hand side, we have a quantum operator now. On the left hand side, we still have a classical property, curvature of a classical space-time. So the approach of quantizing gravity would be to somehow turn this also into some quantum object, basically. And then we talk about quantum objects equating with other quantum objects again, and we can try to make sense of that. The alternative is to say, well, how can we, from this quantum object, from quantum matter, how can we get from quantum matter some property, some classical property that tells us how a classical space-time needs to be curved. And the simplest way to do this is to just take the expectation value of this object. So whatever the quantum state of our matter is, I take the expectation value in this quantum state, and I end up with a classical expression. In this classical expression, I can put back into my Einstein equations, and I have what is called semi-classical gravity, or the semi-classical Einstein equations. So this equation is, for example, the foundation for Hawking's prediction of black hole radiation. So this equation as such is used a lot, but it's usually understood as some limit, actually, like a mean field limit. So a semi-classical limit of some quantum theory of gravity. But now we can also look at this as a more fundamental equation and can just say, well, maybe what if gravity actually works like this at the quantum regime? What if gravity works such that, like, space-time is just a classical property, it's just a four-dimensional manifold, like we know it from classical general relativity, and we somehow have quantum fields living on this manifold, and they just happen to give us gravity. They happen to give us space-time curvature through an equation like this. And there are several things that, from a theoretical perspective, are difficult, and that we don't have the time to discuss in all detail. There are, for example, questions. Then you have to talk about the collapse of the wave function, which we discussed at the beginning. So with such an equation, you run into problems if you want to have a just Copenhagen interpretation, like instantaneous collapse of the wave function. The wave function of a particle just jumps from a spread out wave function to an eigenstate of the position operator. Then this would not work in such an equation. So we need to talk about what is the mechanism behind the collapse of the wave function. So this brings us back to what we discussed at the beginning of the lecture, where we talked about the measurement problem and wave function collapse. We also have to ask the question, and this is also something we discussed at the beginning of the lecture. If we have such an interaction, then we run into this problem: is there a conflict between this and causality? So is this and I should maybe say, so what we get if we start with this equation is exactly what we derived in the previous lecture. So in the non-relativistic limit, from this equation we find this Schrödinger-Newton equation. So I can. So the Schrödinger-Newton equation that we discussed in the previous lecture follows as the non-relativistic limit of this equation. And if you now remember, at the beginning of the course, we were discussing nonlinear Schrödinger equations and how they have problems with causality. So this is another difficulty that we would need to resolve if we want to discuss such a scenario. So on the other hand, if you take quantized gravity, you have the whole problem that we don't know how quantum gravity could make to work, how we can get quantum gravity to work either. So we know, for example, that we have this problem that if you just do the standard approach of perturbatively quantizing gravity, you end up with a theory that is non-renormalizable. So gravity just doesn't work the same way that other field theories work. So in either case, if we treat it semi-classical or in the approach where we quantize gravity, there are open questions, open theoretical questions that need to be addressed. So this is the perspective from theory. As physicists, ultimately we want to know, of course, what we can confirm in the lab, what is experimentally confirmed or testable at least. And from that perspective, we have to say that there is at the current stage, there is just no way of telling which of the two possibilities is true. So the way we currently looks like we have no empirical evidence whatsoever whether or not we need to quantize gravity. And this is the starting point from which I want to start this lecture. So keep this in mind. We have no experimental evidence whether or not we need to quantize gravity. And we have these two scenarios that we want to discuss now. On the one hand, we have the semi-classical approach where we have Einstein's equations with the expectation value of the stress energy tensor. On the other hand, we have the perturbative quantum gravity approach, in which we treat the metric, like a field, and we apply the formalism of quantum field theory to this field. And this we want to briefly discuss now. So perturbative quantum gravity is what we want to discuss now. And for this, I want to first remind you of our lecture number 7, where we discussed the linearized version of Einstein's equations. So this we will need now because essentially what we want to quantize is not the full theory of GR, but we start from the linearized version of gravity. And the first thing you should keep in mind, or you should be aware of, is that this linearized gravity that we had in lecture 7 can also be derived from a Lagrange density as the Euler-Lagrange equations. And this is the so-called Fields-Pauli Lagrangian. So, and the general form, I don't give you the full Lagrangian. You can look it up in the lecture notes. I gave you the full version, but just the general structure is some constant, and then you have terms that are basically derivatives of the metric perturbation h. So remember, we have we write our metric again as sorry, I should. Yeah, we write our metric with some perturbation h around the flat space-time metric. And then the Lagrangian has terms that are derivatives of this metric squared, plus a coupling term between matter and space-time, which is 1/2 T mu nu H mu nu. So if you want to take the Euler-Lagrange equations of this, you would take you would vary the Lagrange density with respect to the fields. So the variation of L with respect to the field H mu nu will give you the T mu nu term. So this will give you the right-hand side of Einstein's equations. And then the second term in the Euler-Lagrange equations is the derivative of the variation of L by the derivatives. So you would vary with respect to these derivatives of H, and then take the derivatives. So this gives you the second order derivatives terms that you have in the linearized Einstein equations. So you will end up with the equation that we had as, so if you look back at lecture number 7, this was equation 713, is the form of the Einstein tensor in linearized gravity. So this is what you get from the variation of this Lagrangian. But for us, what's most important is this term that describes the interaction between space-time curvature and matter at the lowest level. So I should maybe say, so this field's Pauli Lagrangian you can see as the lowest order of an expansion in terms of H. So if you want to get the full Einstein equations and not just linearized gravity, you would need to add higher order terms. So the next order would then be something that is so the next order term you would need to add to this Lagrangian to get closer to Einstein gravity would be something that is proportional or that has as a constant square root g times h times, again, the derivatives of h squared. So this would give you the first order correction terms. And this is where you start running into problems, because if you calculate calculate the mass dimension of this type of term, of these constants, you will find that this has a negative mass dimension. And if you had quantum field theory, then you might remember that terms with a negative mass dimension are usually non-renormalizable. So this is where you then end up with non-renormalizable terms. So we can quantize the linearized version of gravity, and nothing goes wrong in this respect. But if we want to include higher order terms in terms of this metric perturbation, then we run into problems. So basically, the low energy approximation for gravity is fine. The approximation where we have very weak fields. Yeah, but if we actually want to look at higher orders, then we run into problems. That's why it's usually said that you need to go to like the Planck scale, or like situations where you have extreme space-time curvature, like in black holes or in the early universe, to actually see effects of quantum gravity. Because the usual assumption is that, well, if gravity is somehow quantized, then in those regimes that are practically relevant, you can just work with this linearized version, and there nothing weird happens. It only becomes problematic if you want to, from a theoretical point of view, it only becomes problematic when you want to extend this theory to one that is in general situations is compatible with general relativity. So now what we want to do, we have this Lagrangian, and now we just apply the usual formalism of quantum field theory for h mu. So h mu is now our field. So from a classical quantity h mu, we basically promote this to some quantum operator h mu. And we can look at so I give you look at the lecture notes for the equations, but so you can write this h mu. Remember, this h mu is a solution of the linearized Einstein equations. If you look at the vacuum equations that we had in lecture 7, then those are just wave equations. So basically we just had a box h mu equals 0 in vacuum, but we don't have the t mu. So we can just, the solutions of that will just be plane waves. And we can, just like we do in electromagnetism, we can take these plane waves as the modes of our quantum field, and we can expand this operator in terms of these modes. So basically, do an expansion in terms of harmonic oscillators. And again, if you had a quantum field theory lecture, this is what you usually do in quantum field theory. So what you get is you first need to sum over the two helicity modes, the two possible spins of the gravitational field that you can have, which are plus and minus 2. So again, if you look at if you look at these wave equations, what you will find is that you have the possible that you have two helicity eigenstates with eigenvalues plus and minus 2. So basically you have spin 2 solutions, you only have plus and minus 2, you don't have 1 and 0. For the same reason as for the photon, you find only helicity plus 1 and minus 1, because it's a particle, it's a massless particle that travels at the speed of light. So only those two extreme values are permitted. So you would sum over those, and then we have an integral over all the possible momenta of a particle. And now we have a creation operator A that creates a wave of momentum k and spin sigma with some object e mu nu. This is which basically gives us the direction of propagation of this wave. K sigma, and we have the annihilation operator A dagger. With the complex conjugate of this e mu nu. Oh, sorry. K sigma, and so now I forgot, of course. So this one has e to the I kx, and this one has e to the minus I kx. So we have positive and negative frequency modes, just like we would have for the electromagnetic field, and we have these creation annihilation operators that have the usual commutation relation. So the commutator A dagger is a delta function of the momenta and the spins, whereas A with A and A dagger with A dagger commute. So this is the idea in principle behind perturbative quantum gravity. So this is basically quantizing the linearized Einstein equations exactly the same way we would quantize the electromagnetic field, for example. And now with this we can work. So with this we can just do plain boring quantum field theory. What we want to look at next is what this means for the coupling with matter. So now we want to take this T mu nu into account. So if you take the coupling term in the Fields Pauli Lagrangian, you immediately get the interaction. So this term, the term that has T mu nu, H mu nu in it, is the term that will give us the interaction. If you talk about, if you're in quantum field theory, this is from which you will get the Feynman diagram, the vertices in the Feynman diagram, and you can write this as an Hamiltonian just by integrating over space. So the Hamiltonian would be minus 1/2, that's the same constant, and then it is an integral h mu nu t mu nu d3r. So this would be the classical Hamiltonian that belongs to this interaction. And now we can, of course, go to quantum theory and So in perturbative quantum gravity, then we get a Hamiltonian operator, which is simply the operator that we get if we take into account that now both our H mu as a field and our T mu is an operator that depends on our matter fields. So this operator that contains both the H mu operator and the T mu operator, this operator will be the interaction Hamiltonian for our quantum gravity theory. And now we can do what we did so often in the previous lecture. We can ask what is the non-relativistic limit of this, what happens in a laboratory situation. You remember from our discussion of linearized gravity and the Newtonian limit of general relativity that so first of all, that in the Newtonian limit, that the main contribution always came from the 0-0 components. So in the non-relativistic limit, we basically have H00, T00 as the dominant contribution. And now, if you remember, or if you look back into lecture number 7, then you remember that H00 was usually associated with the Newtonian gravitational potential, whereas the T00 component becomes the mass density in a non-relativistic situation. So we have an interaction Hamiltonian here that is just, and the prefactors will just cancel out through this if you do it correctly. So what you get is an interaction Hamiltonian that is the Newtonian gravitational potential phi, phi of r if you want, times the mass density operator, rho of r, integrated over space. And now we can just use the Newtonian gravitational potential. We know the Newtonian gravitational potential is itself an integral of mass divided by the distance. So what we get here is minus g, and then we have a double integral, and we have the mass density, rho of r, and rho of r prime, divided by the distance between r and r prime. d3r, d3r prime. So this is our interaction Hamiltonian in the case of quantized gravity, where the mass density operator, you might remember from an earlier lecture, the mass density operator is rho of r is defined as the mass times the field operator psi dagger of r, psi of r. Okay, so psi dagger and psi are the creation annihilation operators for our field. We will come back to this in a minute. But first we look at what happens in semi-classical gravity instead. And in semi-classical gravity, we start out with the same classical interaction Hamiltonian. But now in semi-classical gravity, all we do is we promote our T mu to an operator, but we leave space-time classical. So essentially, we have semi-classical gravity, we would have a Hamiltonian operator that has a classical space-time metric, h mu nu, with the operator t mu nu. Now the question is, what is this classical space-time curvature? And remember that the source of gravity, the source of space-time curvature, is the expectation value of t mu nu. So in the interaction Hamiltonian, we have the operator t mu nu entering, because this is our quantum field, but we have also the expectation value of t mu nu entering in h mu nu. And you could now go through exactly. You can go through the exact same process that we did with the linearized Einstein equations in lecture 7, and you just replace everywhere where you had a classical mass density or a classical stress energy tensor in those equations, you replace this by the expectation value of your quantum field. So what you end up with is the Poisson equation for a classical gravitational field. Now, not an operator phi, but a classical gravitational field that satisfies the Poisson equation. Laplace operator phi equals 4 pi g times the mass density, which is now the expectation value of the mass density operator. So we can plug the solution of this equation into our Hamiltonian. And again, so in the non-relativistic limit, we get h00 here, so we get basically the solution of this equation as the classical field. And for our t, we will end up just the same way. We will end up with the mass density operator. So what we get in this case is something that looks very similar. It's minus g times a double integral. In the denominator we have the distance between r and r prime, and we need to integrate over r and r prime. But now, instead of having operator rho, we have the operator rho of r, which is our quantum field. But now the space-time curvature is not given by the operator of mass density. The space-time curvature is given by the expectation value of rho of r prime. So this is actually the only difference between our interaction Hamiltonian, is that in the semi-classical case we take an expectation value here, and in the quantum case we have two operators. So now we want to discuss the consequences of this tiny difference in the Hamiltonian. But before we can do this, we need to remember briefly what we did in an assignment earlier in lecture 4. In lecture 4 we discussed collapse models, and in the context of the collapse models I gave you an assignment. I gave you a small exercise where you were considering the mass density operator and the need to regularize this mass density operator. So this is something we need to recall now for a moment. So what we did in the assignment is we showed that if we have the mass density operator, the unregularized mass density operator, and we plug this in to calculate an expectation value in a single particle state for what we now know as the interaction Hamiltonian for quantum gravity. then we get a divergent expression. Okay. So this was what we found in the assignment number 4. So we saw in the assignment that we need to introduce a regularized mass density operator. So instead of this row, this row, we have a regularized row, which is just the mass density smeared with a Gaussian distribution of some width sigma. So this is 2 pi sigma squared power minus 3/2 times the mass times integral d3r prime, and now it's an exponential r minus r prime squared divided by 2 sigma squared and then we have psi dagger of r prime, psi of r prime. Okay. So what we want is we want to use this regularized mass density in the end, and then only in the end for our physical quantities we want to see that those become independent of this width sigma, or at least that they have a well-defined limit as sigma goes to 0. So in the end we want to put sigma to 0 to get back to our actual mass density operator. And with this we have seen that we can calculate these expectation values, and then we need to introduce a renormalized mass. So we get a divergent term then, but this divergent term can just be absorbed in the mass term. So we end up with a renormalized mass, which is the naked mass n plus some mass renormalization delta m, which we found to be minus gn squared divided by square root pi sigma. Okay. So you see that as sigma goes to infinity, this term diverges, but we can just absorb that by redefining the mass. And just also as a reminder, so this was also defined in the exercise, but these n particle states. So a general state for a particle number n is defined as 1 divided by square root n factorial, and then we have to integrate over n variables. So integral of n particle positions with an n particle wave function phi n of these n coordinates. End of time, I avoid time in here because it's not relevant for what we're doing. And then we have creation operators for a particle at each of those positions. So we create a particle at R1 and so on, and we create a particle at Rn. So this needs to be acting on the vacuum state 0. So this is the general representation of an n particle state. And we discussed the one particle state and the expectation value of the one particle state, and we noticed that we need to renormalize the mass and regularize our mass density operator in order to get rid of divergences. And now, after we've established this, we can look at the the expectation value for two particles. So we can calculate this expression, and yeah, I refer you to the lecture notes for an intermediate step. But what you find then is that we can write this again with a divergent term, but which we can just write as 2 times delta n, this mass renormalization. And then the part that survives is minus 2 gm squared double integral, and then we have the two-particle wave function, absolute value squared of the two-particle wave function of R1, R2 divided by R1 minus R2 and this we need to integrate over R1 and R2. So this is, excuse me, this is our two-particle interaction. It's just the Newtonian potential, it's the two-particle wave function, and at all possible positions, at all particle positions R1 and R2 that are with their probability according to the two-particle wave function, we have to take the Newtonian interaction between those two positions. So now let us look at the same for semi-classical gravity. So for semi-classical gravity, we found the interaction Hamiltonian contains the expectation value of the mass density operator. So we would first want to calculate these expectation values, and we can again start with a single particle state, and we also take the regularized mass density operator, take the expectation value in a single particle state and write it with an index 1 here. This is exactly the same we had before, phi 1 rho reg phi 1. And the first thing you will observe if you try to calculate this is that that for the semi-classical case we don't need to regularize the mass density operator. Essentially because you have the wave function, this expectation value, that acts as a regulator already. So the wave function is just fine as a smearing of the mass. So you can just as well calculate the expectation value of the unregularized mass density operator. And you will find exactly the same expression. Namely, you will find that this is the mass times the absolute value squared of the single particle wave function, absolute value squared. And now we can go on and we can also calculate the expectation value in an n-particle state, and what we find is something very similar. This is the mass of our particle, and now we have to sum over all n particles, and we need to take the marginal wave function, so we integrate over all particle coordinates except the I particle coordinate. So we need to sum up all these integrals where we integrate over all coordinates except for one, and this one coordinate is our r. So what we get here is d3 r1 and so on to r minus 1, and then we continue with ri plus 1 up to n, and then we have sorry, this is a typo in the script. If you notice, so this must be the n particle wave function. There is a 2 in the lecture notes, which I need to correct still. The n particle wave function, from r1 to ri minus 1, then the coordinate ri, at the position I we replace by our coordinate r, and then we continue with I plus 1 all the way to Rn. And again, it's the absolute value square. So this is the sum of all the marginal distributions. So basically, if I want to know where the nth part or where the ith particle is in my wave function, then I just integrate over all the other particle coordinates because their position doesn't interest me. So I make use of the fact that their probability is normalized to 1. I integrate over all the other particle coordinates to find the particle coordinate of the ith particle. And now I take, so that this comes in with a mass m, and now I need to sum over all the particles. So this is very intuitive actually if you think about it. And with this we can now calculate our interaction Hamiltonian. Or again the expectation values of our interaction Hamiltonian for semi-classical gravity. And we do this first in the single particle state. So we would have the integral of the mass density operator times the expectation value of the mass density operator. And remember, this was the part that in quantized gravity was divergent. So we needed to regularize this part and introduce the renormalized mass. And then all we got was this renormalized mass term and no interaction at a single particle level. And this is what generally happens in quantum field theory. So at the single particle level, you just get a correction to your constants, mass in this case, but you don't get a single particle interaction. A single particle doesn't interact with itself. And this is very different here, because if you do this, if you actually calculate this, you will find that this expectation value is gm squared and a double integral d3r prime, and now we have the wave function at r. This is basically what comes out from taking this expectation value, and we have the wave function absolute value squared at r prime. This is what comes from taking the expectation value earlier of the mass density operator divided by r minus r prime. And this is exactly what we found before also for the Schwinney-Newton equation. This is a self-interaction of a single particle. So there is now a gravitational interaction term which basically comes from the wave function feeling itself as a mass density. So this is a single particle term that simply is not there in the case of quantum gravity. So if you think back of the Schrödinger-Newton equation, there we had this, we had the single particle Schrödinger-Newton equation that has the self-gravity term, the wave function feeling its own gravitational potential. And if you would take quantum gravity for a single particle, you wouldn't have any gravitational effect. If there is no external gravitational field, a single particle will not feel any gravity. But in semi-classical gravity it does. It feels its own gravitational potential, the space-time curvature that it generates itself. And now we can go to n particles. And we find something very similar, but now we have to sum over all the particles. So again, we find minus gn squared. Then we have to sum both I and j from 1 to n. Then we have integrals over 2n spatial coordinates, so r from 1 to n and r prime from 1 to n. And again, and we find here then the absolute value squared of the n particle wave function with the coordinates r1 to rn, and the same for the prime coordinates. And now divided by the distance, so we sum over I and j here, and so then every term in the sum has some ri and rj prime as a distance. And now if you remember, in the so before we only had the two particle interaction, but so in the quantum gravity case we only had the term r1 minus r2 here. So if we just take n to 2 here, we will find the same. We will have an r1, r2 term. But we sum over all I and j, so we will also have an r1 and r1 prime term here, and r2, r2 prime term here. So we will have self-gravitational terms in addition. So we have the self-gravitation from the particle feeling its own gravitational field, but we also have the mutual gravitation between particle 1 and 2, say. And this becomes a bit more evident at this our next step if we so from this Hamiltonian, which is still at the level of Fock space states, we now go to the representation in the usual Hilbert space picture, where we have the Schrödinger equation for the wave function, and yeah, and in that case, it is quite straightforward to just get the potential that appears in the Schrödinger equation from these Hamiltonians. So what you get for quantum gravity is for n particles is you get an interaction potential that is a sum where I goes from 1 to n, j goes from 1 to n, but, and importantly with the restriction that we only sum over unequal pairs, and we also need to avoid a double counting, so we actually sum only over pairs ij where I is truly larger than j, with the interaction 1 divided by absolute value Ri minus Rj. And this is just what you have also as a potential. For example, when you look at the electromagnetic interaction between multiple particles, you have the position operator here the position operator of the ith particle, position operator of the jth particle, but I and j are separate from each other. There is no self-interaction between for the same particle. And we can do the same for semi-classical gravity. And there we find also have gm squared. But now we truly sum over all combinations of I and j. And we have a slightly more asymmetric situation here. So first of all, we find an integral over coordinates r1 prime up to rn prime, and the wave function in these primed coordinates, so the n particle wave function, absolute value squared divided by Ri minus Rj prime. So this is a completely different situation now. So you have these mutual interactions, but now it's not the particle position that gives you the gravitational effect. So here you have just the position as it comes out from the position operator. Here you have really, as the source of the gravitational field, you have the wave function. So the wave function like a mass density. So this is like a Newtonian potential where you have not a point mass, but you actually have a distribution of mass with some mass density. And this mass density is given by m times the wave function. Yes, and then you have the position operator, the distance between the position operator and some position in your mass distribution here. But you sum over all particles, so you also sum over the pairs where I equals j, where you get the self-interaction where the particle I feels the wave function of the particle Ri. Yeah, so a completely different picture, and keep in mind, so this is so we skipped some steps to get here, but in principle this rigorously follows very basically from the original assumptions we made about how gravity works at the level of Einstein's equations. So the quantum equation follows straightforwardly from the assumption that we start with linearized gravity, we start with the linearized Einstein equations, and we treat h mu nu as a field living on spacetime, and we quantize this field, and we take the interaction term that appears in the Fierz-Pauli Hamiltonian as an interaction between this field h with our matter field, say some Klein-Gordon field living on the spacetime. And on the other hand, the semi-classical approach also follows straightforwardly, but it follows if we take the semi-classical Einstein equations. So we take the Einstein equations with the expectation value of the stress energy tensor of our field. And we can go to step, then go to linearized gravity. We can also derive linearized gravity from the Fierz-Pauli Lagrangian if we want. So we follow the usual steps to derive an interaction, an interaction that enters our Schrödinger equation from this initial assumption. And so the only difference between those two is whether we take the expectation value of T mu nu or whether we quantize H mu nu like a field. So and now, of course, the question is which is the correct one. And again, so philosophically, experimentally, we don't know. Those belong to two different philosophical approaches to what we need to do with quantum gravity. You can like either one more or less. You can find some theoretical arguments that speak for or against the other. And you will find arguments for both and against both. But what we really want to do now is we want to actually find some experimental confirmation. And since we have just two different interactions now for non-relativistic quantum mechanics, there is some hope that we can actually find this. And this will be the topic. This will be the topic of our last lecture, of our final lecture next week, where we will discuss exactly this question. Can we experimentally distinguish between those two types of gravitational interaction in the Schrödinger equation? So I see you next week. Thank you for your attention.